Hello. Hi. Can someone please confirm whether I'm audible?
Yes, sir.
Okay, thanks. We'll start in maybe like 2 3 minutes.
Okay.
Hi. I think only three of us are here. So shall we wait for some more time or shall we start? Is the previous session still going on? Any idea? Maybe we can wait for one more minute. I think it's 7:05. Maybe we can start. Shall we start? or should we wait for some more time? Yeah, maybe we can start. So I'm still audible, right? Okay, I'm still audible, right? Okay, thanks. So we can start. So good evening. My name is Prashok. So I'm doing PhD in IAC Bangalore. So every Wednesday during this time, 7 to 8 p.m., we will be meeting to discuss gate problems on signals and systems, communications, and some more topics in maths. So today we'll be discussing about a method, efficient method to compute DFT. So let's start today's session. So we'll be discussing about fast Fourier transform today. So this fast Fourier transform is an algorithm to compute DFT using less complexity. So this FFT is not exactly a new transformation, but it's a algorithm to compute this. So this FFT is not a new transform, but it's a faster alternative to compute the DFT. So let us recap what is a DFT. So what do we have? Consider a discrete time signal x of n of length n. Now for this signal, we can compute the DFT using the expression that we have over here. So we have x of k to be summation over n x of n e power minus j 2 pi by n k, where k is from 0 to n minus 1. Now the problem with this approach is that if we see this expression here, computing each x of k, we need to do few things. First is that here we have a complex number, here we have another complex number. So this inside term, this involves one complex multiplication. Now if you see the index here, this index goes from 0 to n minus 1. So during this computation of the summation, we need to do n complex multiplication. Furthermore, we need to add all these terms. So if we have n terms, there will be n minus 1 additions. So in short, to compute this expression x of k, we need to do n complex multiplications and n minus n complex additions. Now, what are these things? So complex multiplication is done like this. So we have, let us say, a plus jb and c plus jd are the two complex numbers. Now this multiplication is given by AC minus BD plus J into AD plus BC. So here, if you see, computing one complex multiplication essentially involves four real multiplication and two real addition. Like these four are the real multiplication. These are the real additions. Again, subtraction is also same as addition, so that's fine. Similarly, if you want to add two complex numbers, like let's say a plus jb plus c plus jd, we add the real part and imaginary part separately. That means one complex addition means two real additions. So now what we have seen here, to compute this x of k, this DFT, we need to do n complex multiplication and n minus n complex addition. By the way, if I am going a bit fast or if something is not clear, please let me know. And if my voice is not clear or something, let me know. So I'm going a bit fast because these are not that new. I mean, these are known facts, so that's why I'm going a bit fast. So computing this x of k for each k basically, this requires n complex multiplication and n minus n complex addition. Or in other words, we need to have 4n real multiplication and 4n minus 2 real additions. This is for single value of k. Now if you want to do it for all the k from 0 to k from 0 to n minus 1, we need to do this thing n times. That means computing the DFT essentially require 4n square real multiplication and 4n square minus 2n real additions. Or we can say that it requires order of n square multiplication and additions. Now, when n increases, this n square can get really large pretty fast. So let us say if n is like 100, 100 square is already 10,000. So for large sequences, computing DFT using the usual expression is kind of complicated. So to solve that issue, FFT is an algorithm to do this DFT, this evaluate the same expression but in a smart way. So there are many different variants of this FFT algorithm. There are many different variants itself. Now, one such method to kind of do this computation in a smart way is like this. So again, this is just an overview. This is not a substitute for a course on FFT. I'm just showing few facts here and there so that we can solve the gate questions. So one way to compute. Okay, so till now, is there any doubts or clarification? Shall we proceed? We can continue, no? It's fine. Okay, thanks. Now, let us see this expression x of k summation n equals 0 to n minus 1 xn e raised to minus j 2 pi by n kn. Now, what I'll do is I'll split this into two parts. This indexes goes from 0 to n minus 1. I'll be considering two subsequences, one with odd number of, I mean, terms with n odd and other with n even. So what I'm saying is that here we have x of n. Now we can split this xk into two summations like this, where the first summation is like this: m from 0 to n by 2 minus 1 x of 2m. So if you see the index here, these are basically the even indexed terms. So with a bit of math, we can show that this is basically a DFT itself of the input signal with indices. This is even indices. Similarly, we have the second term here, ABC. This is basically odd indexed terms. So let us call this much as EK and this much as OK. Or let us say, let us GK and HK, that's equal. Let this term be GK and this term be HK. Two different names. What are we doing? We are writing the DFT of the entire sequence as in terms of DFT of smaller sequences. So DFT of the even index terms. This is the DFT of odd index terms. And we have these two combined using some complex number here. So to evaluate this xk, we are splitting xk as DFT of two smaller sequences, this even terms and odd terms. Now, what do? We do this again and again. We have this even terms itself, which will split further, and so on. It will be clear once we see the diagram. Now, this algorithm where we evaluate the bigger DFT by separately evaluating the DFT of odd terms and even terms. This is known as the radix 2 decimation in time FFT algorithm. So this is just a name. Radix 2, this 2 signifies that we are breaking the big signal into two parts. So here this 2 signifies that we are splitting the big sequence into two subparts, and decimation in time is signifying that we are doing this splitting in the input signal itself. Like we are splitting the x of n into even part and odd part. That's just a name that we have. Now there are other algorithms like decimation in time itself with radix 3. There are many other things also, but just to see the idea, we will be focusing right now on radix 2, and while solving questions, we can do something else. Now, here this thing works whenever this n is a power of 2. That's obvious, because if it is not a power of 2, I mean, we can't properly divide into two parts further down. Like, yeah. So why are we doing this? If you recollect, if we evaluate the DFT directly using the expression, we require n square multiplications and additions. Now, if we do this, it is possible to show that we require only n log n. This is again order, actually, order of n log n multiplications and additions. So when n is large, this n log n will be much smaller than n square for large n. Hence, if we compute the DFT using this kind of an algorithm, that will be much faster. That's the idea. So, any doubts now? Shall we proceed? I think it's okay. So let us see what exactly is happening here. So these diagrams, which we often see, these are known as butterfly diagrams. So these are also known as signal flow graphs. So what did we do here? We have, by the way, these pictures are taken from this textbook, Discrete Time Signal Processing by Oppenheim and Schaffer. So for more theory, you can refer to this book or the NPTEL video on FFT. So what do we have? We have this input signal x of n. We are splitting into terms having even terms. Like we see here, we have 0, 2, 4, 6. These are the even terms. These are the odd terms. We take n by 2 point DFT of each of this separately. That is what we are doing here actually. This is a n by 2 point DFT of the even terms. This is n by 2 point DFT of the odd terms. And we are kind of smartly combining them. So what are we doing? We have taking the n by 2 point DFT of the even part, n by 2 point DFT of the odd part, and kind of combine them to get the total DFT. This is what is happening. Now, this n by 2 point DFT, we can again divide further in terms of n by 4 point DFTs. So, what do I mean is that to do this DFT itself, we can split the input like this 0, 2, 4, 6 again into its own odd terms like this. We have 0 and 4 here, and its own even terms. Sorry, this is odd actually. Yeah, onto these two terms like this. So once we do that, we can evaluate this n by 2 point DFT itself using n by 4 point DFTs. That's the idea. So what we do, we started with the big sequence, divide into two parts, use n by 2 point DFT. Now this n by 2 point DFT, we can rewrite in terms of n by 4 point DFTs like this. By the way, I'm just showing all these things. This is not a very proper lecture on FFT, but just to show what is happening, we split it into further two parts and we get n by 4 point DFT. So what do? We keep on doing this till we end up with 2 point DFTs. That's the idea. So we keep on doing this. So the overall picture is like this. We have the input, we have n by 4 point DFT, then we do something over here, something else over here, and so on. So in general, it looks something like this. Finally, we will be reaching the point where we have 2 point DFT. So once we have the 2 point DFT, this is how it looks like. We have two terms, two inputs, and for 2 point DFT, it is very easy. Like DFT of a 2 point sequence will be having e raised to minus j 2 pi by 2k from k equal to 0 to 1. That's very easy. It's just e raised to 0 and e raised to j pi. So that's one is 1, other is minus 1. That's it. So computing this 2 point DFT is very simple that we can do. And what we do is we do the 2 point DFT of appropriate entries. Then we merge them using this kind of a structure. So this might look a bit complicated, but the advantage is that if we do like this, it requires much fewer multiplications and additions. That's the idea. Now, for more details, you can go to the lecture or you can refer the textbook. We might not have time to discuss everything here. So to summarize, for an endpoint f of t, if we don't do anything smart, if we just compute in a DFT, we require n square order of computations. Whereas if we do like this, it requires only n by 2 complex multiplication in each stage. So if you see here, in each stage, this is one stage, next stage, third stage like this. In each stage, it requires n by 2 because if you see here, only very few multiplications are there. So this structure is this thing which can be rewritten like this. I am skipping the details here, but the conclusion is that if we do using this kind of a procedure, in each stage we require n by 2 complex multiplications, and similarly a few complex additions also. And one more thing, if we have n, we will be having log n to base 2 stages. So total complexity, if we do this, will be n by 2 log n to base 2 multiplication and same number of additions. This is approximate, but yeah, that's the idea. So any doubts till now? This is the approximate number. So, and this structure is known as the butterfly structure. So any doubts, any clarifications till now? If it's okay, we can proceed. For more details, you can refer this textbook actually. Shall we proceed?
Sir, what is the video series for this?
What is the
The NPTEL video series.
link? I don't remember directly, but if you search for fast Fourier transform NPTEL, it will be, I think, coming as one of the first results.
Hello.
Hello?
Hello.
Yeah.
Sir, means
Actually, your
NPTEL
voice
series
is
by
not
whom?
very clear. Can you repeat, please?
No.
Hello? Maybe you can type also. Actually, your voice was not very clear for me. Is there any question? Shall we continue?
Yes.
Okay, thanks. By the way, please, the other question I didn't completely hear. Can you please type on the chat, or if there is something else, maybe you can look at it at the end of the video. So this is one type of FFT algorithm. There are many more versions, and other one common variant is known as the decimation in frequency FFT algorithm. So again, I'm skipping the details. It looks something like this. Here again, each of these stages require n by 2 complex multiplications, and there will be log n to base 2 stages. So complexity wise, the whether it is di decimation in frequency or decimation in time, it doesn't really matter. Both of them have the same complexity. Now other thing is like, this is kind of small detail here. So if you see here, the output, if you see the index, it is like in the proper order 0, 1, 2, 3, 4, 5, like that. This is the DFT. Now this is a signal. If we see the index of the signals, x of 0, it's x of 0, it's fine. But for x of 1, here it's x of 4. Or in other words, the ordering here is kind of seemingly arbitrary. But This kind of an ordering is known as the bit reversed order. So yeah, so if we write out the binary representation for these indices, like 0 becomes 000, 1 is 001, 2 is 010, and like that, this sequence is obtained by flipping the order of the bit. So 001 become 100, that is x of 4, and so on. So this is just a consequence of the algorithm. For decimation in time algorithm, input will be in bit reverse order, output will be proper order. Now, if you do the other way around, like decimation frequency, here it's proper order, whereas here it is bit flipped order. These are just some features of this FFT. And for more details, please check the video actually, because it's kind of bit involved. It's a bit too much to cover in one session, and we'll be focusing more on solving questions. So, is it video series given on website? Yeah, actually, I'm not sure about which website, but it should be fairly straightforward. I'll check. Actually, so how do I see? Let me check once. I'm not sure about the which one is that. Mm, let me just check once. F50. I found some links. I not go through it entirely, but yeah, I mean, maybe you can check this one. I'm not very sure. Maybe you can check this one. Or if that's not the link, maybe you can just search on Google. Like even this will do. So shall we continue? Can continue. No? So we'll solve
Yes,
few
sir.
questions. So by the way, this is not a very common area for gate exam. Like only a few questions have came from this area. But the questions that are there are like if you know the theory, it's like doable, not much difficult. So I have two questions with me today, so we can discuss those two questions. If we have further time, we can discuss some other questions, not necessarily from this topic. So shall we proceed to the questions? I understood like the way I explained earlier. It was very short. I mean, it was not a proper explanation because of the lack of time. But yeah, these details you can find it in any online lecture or like in textbook. Like this textbook is pretty good. So yeah, we can move to questions, I think. So what do we have here? So this is the first question. This appeared in 2019 GATE TC paper. So the question is like this. So by the way, this is different from what we have seen till now, but it's still doable. So what they are saying, consider a 6-point decimation in time fast Fourier transform algorithm for which the signal flow graph corresponding to x of 1 is shown in the figure. Let w6 be exponential of minus j 2 pi by 6. In the figure, what should be the values a1, a2, a3 in terms of w6 so that x of 1 is obtained correctly? So they have mentioned that they are using a decimation in time FFT algorithm, but not radix 2. So earlier we are splitting to odd parts and even parts, but here we are not doing that. Here we are doing something else. So what they're doing, they have shown through this graph. Basically, they're splitting the input signal into three different parts instead of two parts. Instead of two parts, they are doing it into three parts, and using these three parts, they are kind of forming a butterfly structure. They're kind of forming a butterfly structure and kind of combining them to obtain the total DFT. What we are asking is, let's represent this A1, A2, A3 in terms of W6. So this is not a direct, I mean, if we just memorize the previous butterfly structure, this will not be working here because that is different. That is for a different 8-point DFT with radix 2. Here we have 6-point DFT and it is radix 3. They didn't mention that, but it's radix 3 because we are splitting the input into 3 parts. So is the question clear? Shall we see the answer? Is there any doubt or clarifications here? Shall we continue? Okay, thanks. So if something is not clear, please let me know. So what are we doing here? We are trying to compute the DFT by separately computing the DFT of this one, and this one in a slightly different way. So what do we have? We have x of k summation n equal to 0 to 5 x of n w6 raised to k, where w6 is e raised to minus j 2 pi by n, where n is 6. So here we first compute 2-point DFTs. We see these are 2-point DFTs. We compute 2-point DFTs of each subsequence. Like this is one subsequence, this is next subsequence, this is the third subsequence. So for each of the subsequence, we will be first computing the 2-point DFT and then we will be combining them in a smart way. So that's what is happening. So here we are splitting the input to 3 parts. We see the index. This is 0, 3, 1, 4, and 2, 5. So we split the input as 0, 3, 1, 4, 2, 5. Separately compute the 2-point DFT and combine them. So we need to find these coefficients a1, a2, a3. So to do that, what we need to do is we need to express this x of k in terms of these indices separately. Like we need to write it explicitly in terms of these indices 0, 3, 1, 4, 2, 5, and so on to see if there is any pattern. So how do you do that? We have x of k to be summation 0, 3, only these two terms, 0, 3, x of n, w6 raised to kn, plus summation n equal to 1, 4, xn, w6 raised to kn, plus n in 2, 5, xn, w6 raised to kn. So what I did, I just rewritten this bigger summation into 3 smaller summations, each summation having 2 terms like this. This is fine, no? Just I explicitly written out the indices involved in the summation. That's it. There is nothing different happening here. So we can write x of k in terms of this is terms with indices 0, 3. This is index 1, 4. This is indices 2, 5. Like that. Now what do we do is we will try to write each of this in a slightly different way. So what do we have? Summation over n 0 to 3 xn w6 raised to k. So n is 0 and 3. So I can do a change of variable. I can write like this: summation r from 0 to 1 x of 3r w6 raised to k times 3r. So I just put n equal to 3r here. This is fine, no? If something is not clear, please let me know. So I just rewritten this summation n equal to 0 to 3 x and w6 raised to kn as summation over r from 0 to 1 x of 3r w6 raised to 3 kr. Now if we note this term, this is w6 raised to 3 kr. What is it? It is e raised to j 2 pi by 6 times 3 kr. This 3 and 6 get cancelled out, becomes 2. That is e raised to j 2 pi by 2 kr, or that is w2 raised to kr. This is fine, no? This is just a rearrangement. So we have this w6 raised to 3 kr to be w2 raised to kr. By the way, so these things might look a bit arbitrary right now, but if you go through the derivation of decimation in time FFT algorithm, the one that we discussed before, the same idea is used there. So this summation can be written like this. What do we have? We have summation r equal to 0 to 1 x of 3r w2 raised to kr. So any doubts till now? Shall we proceed?
Yes.
Okay, thanks. So now this is for the first term here. Now coming to the second term. Again, this is similar. Summation over n 1 and 4 x and w6 raised to kn can be written like summation from r equal to 0 to 1 x of 3r plus 1 w6 raised to k times 3r plus 1. Just like we replace this with 3r, here we are writing 3r plus 1. Now this thing, if we simplify, we can write like w6 raised to k summation r equal to 0 to 1 x of 3r plus 1 w6 raised to 3kr. Again, this guy is w2 raised to kr. So what is this? This summation is same as w6 raised to k summation r equal to 0 to 1 x of 3r plus 1 w2 raised to kr. And this is basically 2-point DFT of x of 1 and x of 4. Similarly, this is basically 2-point DFT of x of 0 and x of 3. Now, similarly, we have the other summation over 2 and 5, x and w6 raised to kn. This can be written like summation from r equal to 0 to 1, x of 3r plus 2, w6 raised to k times 3r plus 2, which can be simplified to be like this. We have w6 raised to 2k, summation r equal to 0 to 1, x of 3r plus 2, w2 raised to k. And this case basically the 2-point DFT of x of 2 and x of 5, these two terms. So what do we have? We have the overall summation x of k to be summation r equal to 0 to 1 x of 3r w2 raised to kr plus w6 power k times summation r equal to 0 to 1 x of 3r plus 1 w2 raised to kr plus w6 raised to 2k, again 0 to 1 x of 3r plus 2 w2 raised to kr. Now if you see this diagram here, what are we doing here? We to compute this x of 1, we are combining the 2-point DFTs of this sequence, this part and this part using a1, a2 and a3 respectively. So if we just substitute k equal to 1 in this equation, we can see that what is happening. X of 1 is summation r equal to 0 to 1 x of 3r w2 raised to r plus w6 times summation r equal to 0 to 1 x of 3r plus 1 w2 raised to r and plus w6 square summation r equal to 0 to 1 x of 3r plus 2 w2 raised to r. Now this term here, this whatever signal coming here, this is what this is, this whatever summation we have here, that is the value in this node. Actually the signal coming in this node, that will be x of 0 plus x of 3. I think there's a negative in between, that's it, this one. So that is what is happening here in these two terms. Now similarly, the value in this node is basically this term here. It's easy to see because here it's like 0 and 3, these two terms. R equal to 0 will be having x of 0, r equal to 1 will be having x of 3. So we are combining these two like this. So what we have here in this point, that is same as what we have here. That's okay, right? Shall we continue?
Yes.
Okay, thanks. So again, what we have here, this is x of 1 and x of 4. That is precisely what we have here. And similarly, we have x of 2, x of 5. We are combining it here. This term in this node is exactly what we have here. So this total term x of 1 is what we have here times a1 plus what we have here times a2 plus what we have here times a3. But if you see the expression, what do we have? X1 is what do we have here times 1. This is 1 here plus w6 times what do we have here? this term, plus W6 square times what do we have here. Or in other words, what it means is that if we do a comparison, A1 will be 1, A2 will be W6, and A3 will be W6 square. That we obtain by comparing this signal flow diagram and this expression that we have over here. Which means that our option, correct option is C. So option C is the correct answer. So any clarifications here? Shall we proceed to next question? I have one more question on f of t. After that, we can do some other topics. So in the last 10 years, I think these two are the only questions that came from this topic. I was not able to find any other top question in the same topic. But yeah, any
Yes,
clarifications?
yes, yes, sir.
Okay, thanks. So this is the next question. This came in 2016 GATE paper. So the question is like this: a continuous time speech signal xt or xat is sampled at a rate of 8 kilohertz, and the samples are subsequently grouped in blocks each of size n. The DFT of each block is to be computed in real time using the radix 2 decimation frequency FFT algorithm. If the processor performs all operations sequentially, means one after other, and takes 20 microseconds for computing each complex multiplication, that includes the multiplication by 1 and minus 1, and the time required for addition subtraction is negligible, then what is the maximum value of n? So what it is saying is that we have some input, some speech, we sample it, we get x of n, let us call this x of t, and we need to group it into blocks of n. So let us say x of 0, x of 1 up to x of n. We have a block of n. I need to do the n point DFT. So the data keeps on coming. I'll group it into a block of n. I'll do the DFT to do something else. But the key point here is that this should be done in real time. So, so yeah, where is that given? Yeah, DFT of each block is done in real time. So we don't know what is this n. So the question saying is that how large can this group be so that we can still compute the DFT in real time. So is the question fine? Is it okay? This is the question. So any doubts in the question? Shall we proceed to the answer? We can proceed, right?
Yes, yes,
Okay,
sir.
thanks. So what do we have in each stage of this decimation in frequency FFT algorithm? In each stage, we need n by 2 complex multiplication. This is the key fact. So how are we getting that? If we see the signal flow graph of this decimation in frequency FFT, in each stage, like these are different stages. In each stage, we need to have n by 2 complex multiplications. So if we see this part, we have 1, 2, 3, 4. So we have 8. That means n by 2 multiplication by wn's. In addition, there will be a few multiplication with minus 1 and 1, which we ignore. But the main complex multiplication, the one with wn power 1, 2, 3, 4, these things, In each stage, we will be requiring n by 2 of them. So here we have n equal to 8. Here in this stage, we have 4 multiplications here. This stage, we have 4 multiplications here. Here we have 4 multiplications here. So n by 2 complex multiplication in each stage. That is the number of computations that are needed in this decimation frequency f of t. So that is clear, right? So in each stage, we need n by 2 complex multiplication. In addition to that, there will be few more multiplications with 1 and minus 1, and there will be some additions. So it is given that this 20 already contains the time taken for this small multiplications 1 minus 1, and the time for addition and all that can be neglected. We basically need to only find how much time it takes to do this n by 2 complex multiplication in each stage. That's the idea. So it's okay till now, right? So what do we have? It's given that the sampling rate is 8 kilohertz. So duration per sample, which is TS, which will be 1 by Fs, that will be 1 by 8 kilohertz or 125 microseconds. Now the data is coming continuously. We are sampling it and getting the samples x0, x1, like that. Now time required to form a block of n samples. This will be n times duration per sample, NTS. Now this value, this n by 2 complex multiplication, this is for each stage. And for n point f of t, there will be log n to base 2 stages. So what does it mean? Total number of complex multiplication is n by 2 log n. That's the idea. So so when I say complex multiplication, these are the actual complex multiplication. We ignore the time taken for this plus 1 minus 1 multiplication and all. So total number of complex multiplication for the entire DFT is n by 2 log n. How we are getting this? N by 2 for each stage and log n stages. It is also given in the question that each complex multiplication requires 20 microseconds. So total time required to compute the n point f of t is n by 2 log n times 20 microsecond. This is the total time taken to compute the entire DFT. So till now it's okay, right? I think it's fine. So what is the question? We need to do this thing in real time. So the input is coming, and along with the input, we are computing the f of t. So we don't know what is this value of n, and we are asked to find what is the maximum value of n. So the catch here is we need to do this operation in real time. That means the time to compute f of t should be less than or equal to the time to gather those n samples. So if this is satisfied, by the time we get this n samples, we can do f of t, do whatever we want to do with that. Then we can wait for the next batch of n samples. So to make sure that we can do real time processing, the total time required to compute f of t should be less than or equal to the time to gather n samples. So this argument is okay, right? Is there any doubt here? Shall we proceed? Okay, right? So what do we have? Time to compute f of t is n by 2 log n times 20 microsecond. And time to gather n samples is n times 125 microsecond. We just need to find what is the maximum value of n so that this is satisfied. So this we can simplify like this. Log n to base 2 less than equal to 125, or log n to base 2 less than equal to 12.5. And by the way, this should be an integer. So n should be an integer. And this log n to base 2 also should be an integer. Because this is basically the number of stages. So let us take the largest integer less than 125. which is 12, log n to base 2 is 12, or n is 2 power 12, or 4096. So this is the maximum value of n, so that we can process in real time. So the correct answer is 4096. So any clarifications here? Any doubt? We have 10 more minutes. So this only these two are the gate questions that I was able to find out in the last 10 years, 10, 12, I think, years regarding this FFT. So if any other question is there that you might know, we can discuss that. Otherwise, we can go to the FFT. So we still have 10 minutes. So there's a small topic that we can cover in that. So any doubt till now? Shall we proceed? Can continue, right?
Yes, sir.
Okay, thanks. So we'll move on to the next topic. So this is not related to what we did till now, but this is a very small topic. Like we don't need an entire session for this. I was supposed to cover this during the class on Laplace, but yeah, this is fairly easy. So I'm going to present two theorems. I'm sure that all of you might be already aware of these things. So these are known as initial value theorem and final value theorem. So let x of t. By the way, is there any clarification, anything till now? Whatever I'm discussing now is totally different from what we had till now. So f of t, that is already over. So those two were the questions I was able to find out in last 10 years. So this is something different, but we still have time for this. We can solve one question on this topic maybe. This is common. Like there are many questions on these two topics. I was supposed to discuss during Laplace transform, but we didn't get time at that time, so we can discuss it now. It won't take much time. So we can continue now.
Yes, sir. Continue.
Okay, thanks. X of t is a continuous time signal, and x of s is the Laplace transform of t. This is the setting. Now, these two theorems allows us to calculate what is known as the initial and final value of the time domain signal. So, this is the initial value theorem. What it says is that limit of t going to 0, s of t is given by limit of s going to infinity, s times x of s. This is the time domain signal. I'm still there, right? I think there was some issue with internet in between. Okay, so this is the time domain signal, and this one is the frequency domain, the Laplace transformation. This is known as the initial value theorem. Similarly, we have the final value theorem, which is again limit of t going to infinity x. This is same as limit of s going to 0, s times x of s. Now, there are a few conditions that if you want to apply these theorems, these limit should exist in the first place. So if there is no limit, then we can't really do anything. And for this final value theorem, all the poles of this s times x of s should be on the left half plane. Otherwise, we can't do this. Or if you apply, we might get values like infinity and things like that. So apart from the usual things like these limits should exist in the first place, the theorem is more or less straightforward. The initial value is given by limit of s going to infinity s x x, whereas the final value is given by limit of s going to 0 s times x of s. So these are theorems. Theorems are pretty straightforward. Only thing is that we should make sure that these limit actually exist. If the limit doesn't exist, then we can't apply this. So any clarifications? We have time for one question, maybe one or even two questions. Questions are pretty simple here. So shall we continue? Okay, thanks. Okay, so this is the first question. This is a bit old. I mean, there are newer questions also, but yeah. So the question is like this: given that f of t, the time domain signal, is the inverse Laplace transform of this 3s plus 1 by s cube plus 4s square plus k minus 3s. This is given. Now, if limit of t going to infinity f of t is 1, what is the value of k? That's the question. So this is an application of the final value theorem. So what do we have? Given t is like this, f of t is like this. So let us call this thing to be f of s. So what do we have? Given f of s to be 3s plus 1 by s cube plus 4s square plus k minus 3s. Now, limit of t going to infinity, f of t is 1. We need to find what is k. Question is fine, no? There is any doubt or clarification, please let me know. So we from final value theorem, what do we have? Limit of t going to infinity, f of t is same as limit of s going to 0, s times f of s. What is this? Limit of s going to 0, s times f of s is 3s plus 1 by s cube plus 4s square plus k minus 3s. I can take one s common from denominator. Is your gone, and it is given that this guy, this is 1. So limit of t going to infinity, f of t is 1. That means this is 1, or 1 equal to this. Or what I can say is that limit of s going to 0, 3s plus 1 by s square plus 4s plus k minus 3. This is 1. So I can apply the limit here. Putting s equal to 0, I'll be having 1 by s, this is 0, this is 0, this is 0. 1 by k minus 3 is 1, or k equal to 4. So this is the solution. So correct answer is option D. So this is okay. Any doubts? Any clarifications? K equal to 3. K is 4, right? Okay, that's fine. That's fine. Okay, so we have one more quick question. This is very simple. So question is like this. This is a old question, but this is a tricky question. So it's very easy to do. Consider the function f of t having Laplace transform f of s like omega naught by s square plus omega naught. This is the condition for stability. That is fine. What is the final value? Any guesses? This is the signal f of s. We need
T.
Laplace transform. What is the final value? So by theorem, what is f of t? F of infinity will be limit of s going to 0, sfs. If we put s going to 0, sfs, we might. What is the final value basically? Any guess? So if you see here, this sine omega naught t is having the Laplace transform omega naught by s square plus omega naught square. Now, if we evaluate this thing, what will we get? Limit of s going to 0, sfs is limit of s going to 0, s omega naught by s square plus omega naught square. So this will come as no, that's the problem. So this s will get cancelled out, right? Limit of s going to 0, omega naught by s plus omega naught square by s something. This is problematic. This will go to infinity. 1 by 0. So this we might get the value is infinity. So D is the answer. Correct? Any suggestions? Anything there? If I say that D is the correct answer, is it correct? It is not
No,
correct.
sir.
It's not correct. Actually, answer is C. It's not correct. Why is that so? Because what is a signal actually? Signal is like sine omega not t, sine wave. So it will keep on oscillating like this. There will not be any final value. When t goes infinity, we can only say that it lies in this interval. We can't say whether this is 0, 1, or infinity. Of course, infinity won't happen because this limit doesn't exist. That's the reason why it's not coming properly. So in SFS, it's yeah. So we can't just blindly apply the theorem everywhere. So here, time domain signal is f of t. So C is the correct answer, not D. Any clarifications? So we need to make sure that when we're applying this theorem, that it setting kind of makes sense. So we can't always just use the theorem and get the answer. So the correct answer is option C. So any doubts or clarifications? I think it's 8 o'clock. So
So what will be the next topic?
next topic is linear algebra next week. Max topic. Some topics in eigenvalues and some questions on some solutions of linear equations, something like that, like some questions in linear algebra. So any doubts? If not, we can pause for the day. Thank you. Thank you very
Thank you,
much for
sir.
attending. Thank you.
Thank you, sir.
Sir,
Yeah, yeah.
sir,
Yes.
sir, what is your email address?
Yeah, 1 second. Yeah.
Thank you, sir.
Okay. Okay then. Thank you. Thank you very much. So okay. See you next week. I'll be ending the meeting. Thanks for ending. Thank you.